All right, so we're going to move now, and we're going to talk about what Newton was really most famous for was understanding gravity, at least the attraction between bodies of mass. And so that's what we're going to be talking about today, universal gravitation. So imagine that we had a mountain on Earth, and we shot a cannon ball off the top of the mountain. Now imagine that when you shoot that ball, it's going to rise and it's going to fall. And that's because it has a horizontal component and a vertical component, right? It's got a Vx and a Vy. If we were to make that have more speed, right, it would rise higher and it would fall further. And it would have an X component and a Y component. Remember that the Y component would decrease at the top here, but at the same time, the X component is always staying the same. So what Newton realized was that the moon was really falling around the Earth, and the reason he knew this is because he did this thought experiment. He said, "What if we had thrown this at a big enough speed that when it reaches the top, it never can fall back to the Earth, and instead it starts taking, it's orbiting the Earth. It never can come back and land on the Earth because the Earth is curving away from it. It has more eccentricity in its curve than the path of the ball does, and that would be because you gave it some upward speed, but you gave it enough forward speed that it would just keep propelling itself forward. And we now know that speed that is tangent to the path is called tangential velocity. And what he did is he picked 2 points on that projected circle and he measured how far there was between, in the vertical direction between those two velocities. And he was able to prove that the moon was falling at the same rate downward that an apple was falling. And so for this reason, he said that the moon had enough tangential velocity to keep it propelling forward. Okay? And it never does get the ability to fall back down to the Earth. And that's what's keeping it moving around in a circle. So this moon is undergoing uniform circular motion. There is a centripetal force that is causing it to fall around the Earth. And he was able to propose the idea of universal gravitation, that the centripetal force that caused the moon to stay in orbit was equal to the gravitational force between those two bodies. So he had to actually come up with calculus, the derivative, to be able to prove his theory. But in just what he came up with was this formula that could be used to find the attraction of the moon to the Earth. And he also realized, because he understood that for every action there was an equal and opposite reaction, that if the Earth was pulling towards the moon, if the Earth was pulling the moon towards it, the moon was pulling equal and opposite. So these forces have the same magnitude, they're just in opposite directions. And that is called the gravitational force. So turns out that if you were to increase the mass of either one of these, the force of attraction would increase. So there's a direct relationship between mass 1 and mass 2. But there is an indirect relationship between r squared. And what that means is that if you double r, then the inverse square will happen to force. It'll be 1/4 as big. If you triple r the distance, then that force of retraction will be 1/9 as much. And if you cut the radius in half, the inverse of 1/2 is 2, and 2 squared is 4 times as much. So the closer these objects get, the stronger the attraction. And so the formula is equal to a constant called the universal gravitational constant, 6.67 times 10 to the negative 11, times the masses in kilograms divided by r squared, the distance between them in meters. So if I wanted to find the gravitational force between two objects, it would be simple. Let's draw a picture of what's going on. M2 is attracting, is pulling M1, and M1 is pulling on M2, and those two forces are equal to Fg equals G M1 M2 all over R. Well, G is 6.67 e to the negative 11 newtons meter squared all over kilogram squared times 4 kilograms times 40 kilograms. And notice that our constant is in meters. So when we plug in for r squared, it's going to be 0.04 squared meters. So if we put this in our calculator, 6.67 exponent negative 11 times 4 times 40 equals, divided by the quantity, 0.04 in quantity, actually 0.04 squared equals, and in scientific notation, let me just find a scientific notation for that. It's 6.67 e to the negative 6 newtons. So that would be the attraction. So if you wanted to find the gravitational force between any two objects, it's really simple. You need to know the mass of them and the distance between them. So as long as you know the mass of them, so you could do the sun and the earth, you would need to find and look it up on a chart, the mass of the sun, the mass of the earth, and look up the orbital radius of this between those two and square it. And that would give you basically that attraction between the sun and the earth. And remember that if it's an attraction, they're both pulling on each other with the same amount of force. So the other thing you need to understand is that this is this relationship between distance and mass. So, for example, if I wanted, in this first situation, if I had these two masses in this distance, be 6 times 10 to, okay, so first of all, I got to put my constant in there, 6.67 e to the negative 11 newtons meter squared all over kilograms squared, times 6e to the 24 kilograms times 100 kilograms divided by the quantity 6.4 e to the 6 squared. So let's try to do this. All right. Move this over so I can see my numbers a little bit better. Okay, I've got sorry, I just lost it. Let me find it again. All right. 6e to the 24, 6.67 exponent negative 11 times 6e to the 24 times 100 equals, divided by the quantity, 6.4 exponent 6 squared in quantity equals. And I'm getting Fg is equal to 9.77 e to the 2, or 977 newtons. So this would be 977 newtons. So now let's look at what I've done here. This second column, I'm going to have the same mass and the same masses, so nothing's going to change there, but I'm going to double the distance. Well, if you double the distance, the inverse of that is 1/2, so it's going to be 1/2 is 1/2 squared, or 1/4 of 977. And 1/4 of 977 divided by 4 is 244. So 244 newtons. And if I triple it, right, it's going to be 977, and the inverse of 3 is 1/3. I square that, it's 1/9. It's going to be divided by 9. So only be 109 newtons. And if I instead cut the distance to 1/3, inverse of 1/3 is 3, 3 squared is 9. So 9 times 977 is 8790 newtons. So it's that simple. You don't even have to plug in all these numbers again. You can just use the inverse square. So what do we know about gravitational force and centripetal force? So if we have, let's go back to the Earth here and the moon, right? The moon has a tangential speed that's causing it to stay in a circle. And that centripetal force that's causing it to stay in the circle is the gravitational force. Well, the centripetal force would be the mass of the moon times its velocity squared divided by the orbital radius of the moon around the Earth. And that would be equal to big G times mass of the moon times mass of the Earth all over R orb squared. So you notice that the mass of the moons go away, and one of this R will go away, and one of these R's will go away. So you'll end up with V squared equals G times mass of the Earth all over R of the orbit. And this V is that tangential velocity, and it's really the escape velocity for the Earth. If you go faster than this velocity, then you can escape the gravitational field and leave the orbit of the Earth. But if you don't go faster than that, then you will fall back down to the Earth. You won't make it in the orbit. So if I wanted to know what this speed was, I would need to look up the mass of the Earth, the radius of the Earth and the moon, and solve for V.